Let's design Chapter 26, Real-Time Gaming Leaderboard. Starting with our functional requirements. The core feature we need to support is displaying the top 10 players on a leaderboard. Beyond that, we need to be able to show a specific user their own rank, even if they're not in the top 10. And as a bonus requirement, we'd like to display the 4 players immediately above and below a given user, giving them some local context around where they stand. Now let's walk through the clarifying questions, because the answers here will heavily shape our design. First, how is the score calculated? In this system, a user earns 1 point every time they win a match. Simple and clean. Are all players included on the leaderboard? Yes, every player is eligible. Is there a time boundary associated with the leaderboard? Yes, each month a new tournament begins, which resets and starts a fresh leaderboard. That's important because it means we don't need to accumulate scores indefinitely. Can we focus only on the top 10 users? The primary goal is displaying the top 10 along with the position of a specific user. Showing the players surrounding a particular user is a nice-to-have if time allows. How large is the user base for a tournament? We're looking at 5 million daily active users and 25 million monthly active users. How many matches does each player play? On average, 10 matches per day. What happens when 2 players have the same score? They share the same rank. Tie-breaking logic is out of scope for now but can be revisited if time permits. And finally, does the leaderboard need to be real-time? Yes, we need to reflect score updates as close to real-time as possible. Batched or delayed results are not acceptable. Moving into our non-functional requirements. Given the real-time constraint from our clarifying questions, score updates need to be reflected on the leaderboard immediately as they happen. On top of that, we need the system to be generally scalable, available, and reliable, the usual pillars of a robust distributed system. Now let's do some back-of-the-envelope estimation to ground our design in real numbers. With 5 million DAU, if we assume an even distribution of players across a 24-hour period, that gives us roughly 50 users online per second. But traffic is rarely even, accounting for peak load, we can estimate around 250 concurrent users per second at peak times. For right QPS, that is, users scoring a point, each user plays about 10 matches per day, so at average load that's 50 users per second times 10, giving us 500 QPS. At peak, that jumps to 2500 QPS. For read QPS, fetching the top 10 leaderboard, if we assume each user checks it once a day on average, that's about 50 QPS, which is quite manageable. Now let's think about Redis storage estimates. In the worst case, all 25 million monthly active users participate in a given month. If each user entry consists of a 24-character string ID and a 16-bit integer score, that's about 26 bytes per user. Multiply by 25 million and you get roughly 650 megabytes of storage. Even if we double that to account for the overhead of a skip list data structure, this comfortably fits within a modern Redis cluster. It's also worth noting that 2,500 write operations per second is well within the capabilities of a single Redis server, so our update throughput is not a concern at current scale. Now, what about scaling Redis storage if the product grows? At 5 million DAU, a single Redis instance handles both storage and QPS without issue. But imagine the user base grows tenfold to 500 million DAU. Storage would balloon to around 65 gigabytes, and QPS would reach 250,000. At that scale, a single instance would no longer suffice, and we would need to introduce sharding across multiple Redis nodes. Now let's walk through the core entities. Starting with a leaderboard entry, this is the fundamental unit of data we're working with. Each entry has a user ID, which is the unique identifier for a player, a username or display name for showing on screen, a score represented as an integer for total points earned, and a rank which is the player's current position on the leaderboard. Moving on to the leaderboard itself. The leaderboard is scoped per monthly tournament, so each tournament gets its own isolated leaderboard. It holds a ranked list of all participating players for that period. Next is the user profile. User profiles are stored in MySQL and contain the core user details like username and display name. This is your standard relational data that doesn't need any special treatment, MySQL handles it well. Then we have the game result, also called a win event. This records the moment a user wins a game. It's stored in a supporting MySQL table, and importantly, it serves as a source of truth that can reconstruct the entire leaderboard if something goes wrong with your infrastructure. That's a critical durability property. You're not just relying on an in-memory or derived state. Now for the leaderboard table in a relational model. This is what the data looks like structured in a traditional SQL table, rows representing players with their scores and ranks stored directly. Finally, the sorted set in Redis. This is the key data structure powering real-time leaderboard functionality. Internally it uses two complementary structures, a hash map that maps each user ID to their score, and a skip list that maps scores to users in sorted order. The skip list is what makes Redis sorted sets so efficient. It allows fast insertions, updates, and rank lookups all in logarithmic time, which is exactly what you need when scores are changing constantly across millions of players. Let's walk through the API design. We have three endpoints to cover. The first is a post to /v1/scores. This is how a user's score gets updated after they win a game. It takes two parameters, a user ID and the number of points earned. One important thing to call out here, this endpoint should only be accessible to game servers, not to end clients directly. You don't want players being able to submit arbitrary scores from their own devices. That's a security concern, so you lock this down at the server level. The second endpoint is a get to /v1/scores. This is how you fetch the top 10 players on the leaderboard. The response comes back as a data array where each entry includes the user ID, the username, their rank, and their score. So for example, Alice might be sitting at rank 1 with a score of 12,543, followed by Bob at rank 2 with 11,500. The response also includes a total field confirming you're getting 10 results back. The third endpoint is a get to /v1/scores/user ID. This lets you look up a specific player rather than the full leaderboard. The response returns that user's ID, their score, and their current rank. So if you need to show a logged-in user where they personally stand, say user 5 is at rank 6 with a score of 1000, this is the endpoint you'd call. Let's walk through the data flow section. Starting with what happens when a user scores a point. When a player wins a game, the client sends a request to the game service. The game service first validates whether that win is actually legitimate, and then calls the leaderboard service to update the player's score. From there, the leaderboard service writes the updated score into the leaderboard store. Fetching the leaderboard is simpler. The player makes a call directly to the leaderboard service to retrieve leaderboard data, for example, the top 10 players, or where a specific player currently ranks. Now let's look at the Redis operations that power these flows. When a user scores a point, we run Zinkerby leaderboard _February_2021 1, Mary 1934. This atomically increments Mary 1934's score by 1 in the sorted set. Notice the leaderboard key includes the month. A new leaderboard is created every month, while older ones are moved to historical storage. When a user wants to fetch the top 10 players, we run srivrange leaderboard _February_2021 09 with scores. This returns elements from the sorted set in reverse order, highest score first, giving us back something like a list of user score pairs, for example user 2 with their score, user 1 with theirs, and so on. What about fetching a specific user's position on the leaderboard? If we know a user sits around position 357, we can retrieve the surrounding window with srivrange leaderboard _February_2021 357 365. And to find that position in the first place, we use srevrank followed by the user ID. Redis handles this efficiently because the sorted set data structure is designed exactly for ranked retrieval. Now let's look at how the same operations would work with a relational DB. When a user wins a point against a relational database, the logic branches depending on whether the user already exists in the table. If they don't, we insert them first. Insert into leaderboard, user _ID, score, values, Mary 1934, 1. On all subsequent calls, we just increment their existing score. Update leaderboard set score equals score plus 1 where user _ID equals Mary 1934. Now for finding the top players of a leaderboard with a relational database. A naive query uses a row number variable to assign ranks, orders everything by score descending, and returns the results. Select @rownumber equals @rownumber plus 1, AS rank, user underscore ID, score from leaderboard order by score desk. The problem here is that this performs a full table scan to sort every record in the database. That doesn't scale. We can improve it by adding an index on the score column and using a limit clause. Select @rownumber equals @rownumber plus 1, AS rank, user underscore ID, score from leaderboard order by score desk limit 10. This avoids scanning the entire table when you only need the top results. However, this approach breaks down when you need to locate a user who isn't near the top of the leaderboard. Finding an arbitrary rank still requires scanning through a large portion of the data, which won't perform well at scale. Slide _1. Let's walk through the high-level design. Starting with the high-level architecture. When a player wins a game, their client sends a request to the game service. The game service first validates that the win is legitimate, and then calls the leaderboard service to update that player's score. The leaderboard service takes that update and writes the new score to the leaderboard store. Separately, when a player wants to see the leaderboard, they make a call directly to the leaderboard service to fetch data, for example, the top 10 players, or their own current rank. Now, an alternative design was considered where the client updates their score directly within the leaderboard service, bypassing the game service entirely. This might seem simpler, but it's a security problem. It's susceptible to man-in-the-middle attacks. A player could place a proxy between their client and the server and freely manipulate their score. So we reject this approach. One additional caveat worth mentioning: for games where the server itself manages the game logic, clients don't need to explicitly call the server to record a win. The server handles that automatically based on what happens in the game. There's also a question of whether we should introduce a message queue between the game server and the leaderboard service. This would be valuable if other services downstream are interested in game results. However, that's not an explicit requirement at this stage of the interview, so we're leaving it out of the design for now. Slide _2. Now let's move into data models, specifically the options we have for storing leaderboard data, relational databases, Redis, and NoSQL. The NoSQL solution will be covered in the deep dive section, so here we'll focus on the first two. Starting with the relational database solution. If scale isn't a concern and the number of users is relatively small, a relational database serves us quite well. We can start with a simple leaderboard table structure. There's additional data that could live in this table, but it's irrelevant to the queries we'd actually run, so it's omitted for clarity. Moving on to the Redis solution. The motivation here is finding something that holds up well even for millions of players, without falling back on complex and expensive database queries. Redis is an in-memory data store. It's fast precisely because everything lives in memory, and it has a data structure that fits our use case perfectly, the sorted set. A sorted set is similar to a set in most programming languages, but it keeps its members sorted by a given score. Internally, it uses two structures working together: a hash map that maintains the mapping between a key, in our case, the user ID, and their score, and a skip list that maps scores to users in sorted order. Which raises the question, how does a skip list actually work? It's a linked list designed for fast search. It consists of a base sorted linked list combined with multi-level indexes layered on top. This structure lets us locate specific values much more efficiently as the dataset grows. To illustrate, with 64 nodes, finding a value in a plain linked list requires traversing up to 62 nodes. With a skip list, that same search takes only around 11 nodes. The multi-level indexes let you skip large portions of the list in a single jump. Sorted sets are more performant than relational databases for this use case because the data is always kept in sorted order. The trade-off is that insertions and lookups cost log n time, but that's a very acceptable trade-off. By contrast, here's what the equivalent query looks like in a relational database to find the rank of a given user. It's a nested query. You're counting how many users have a score greater than or equal to the target user's score. This kind of query gets increasingly expensive as the table grows. So what are the specific Redis operations we need to run our leaderboard? First, ZADD, This inserts a user into the sorted set if they don't already exist, or updates their score if they do. O, log n, time complexity. Second, Zincreby, this increments a user's score by a given amount rather than setting an absolute value. If the user doesn't yet exist in a set, their score starts from 0. Also O, log n. Third, Range and Range, these fetch a range of users sorted by their score. You can specify the ordering, ascending or descending, as well as an offset and a result size, which is exactly what you need to serve a top 10 leaderboard or paginate through rankings. Now let's move into the deep dive section, where we examine the more nuanced decisions in this design. The first topic is whether to use a cloud provider or not. This is a fundamental infrastructure choice. We can either deploy and manage our own services, handling all the operational overhead ourselves, or we can lean on a cloud provider to manage that infrastructure for us. The right answer depends on your team's capabilities and your product's requirements, but it's always worth calling out explicitly as a design consideration. The second deep dive is on scaling Redis. At 5 million daily active users, we can comfortably get away with a single Redis instance. Both storage requirements and query per second load are manageable at that scale. But imagine the user base grows 10 times, to 500 million daily active users. Now we're looking at around 65 gigabytes of storage and 250,000 queries per second. A single instance simply can't handle that, so we need to think about sharding. One approach is range partitioning, where we divide data into ranges based on value. In this design, we shard based on a user's score. We maintain a mapping between each user ID and the shard they belong to, and we can store that mapping either in MySQL or in a separate cache. The key benefit here is that fetching the top 10 players is straightforward. We just query the shard holding the highest scores, say the 900 to 1000 range. Fetching a user's rank is slightly more involved. We calculate the rank within their shard, then add the count of all users with higher scores across the other shards. Fortunately, that second part is an O of 1 operation, because the total record count per shard is immediately accessible via Redis info keyspace command. The alternative is hash partitioning, which you can achieve using Redis cluster, a proxy that distributes data across nodes using an approach similar to, but not exactly the same as, consistent hashing. The problem with this setup becomes clear when you need to fetch the top 10 players globally. Because data is spread based on a hash rather than score ranges, you have no guarantee that the highest scoring users are all on the same shard. So you'd have to pull the top 10 from every shard and merge the results in application code. This creates a few real limitations. If you need to fetch the top K users where K is large, latency grows because you're pulling significant data from every shard. Latency also increases as you add more partitions. And there's simply no clean way to determine an individual user's absolute rank. For all these reasons, the author leans toward fixed range partitions for this problem. A couple of additional caveats worth noting. It's best practice to allocate twice as much memory as you actually need on write-heavy Redis nodes, to accommodate snapshotting. And you can use a tool called Redis Benchmark to measure the performance of your Redis setup and make data-driven decisions rather than guessing at capacity. The third deep dive is an alternative solution using NoSQL. Rather than Redis, you could choose a NoSQL database optimized for heavy writes and for efficiently sorting items within the same partition by score. DynamoDB, Cassandra, and MongoDB are all reasonable fits. The author chooses DynamoDB here. It's fully managed, offers reliable performance, scales well, and supports global secondary indexes for querying fields that aren't part of the primary key. Let's walk through how the table design evolves. We start with a basic leaderboard table for a chess game. This initial design works, but it doesn't scale well if you need to query by score. So the natural fix is to make score a sort key. That helps with score-based queries, but introduces a new problem. We're partitioning by month. The most recent month will receive a disproportionate amount of traffic compared to older months, creating a hotspot partition. To address this, we can apply a technique called right sharding, where we append a partition number to each key, calculated as the user ID modulo the number of partitions. This spreads writes more evenly, but it introduces an important trade-off around how many partitions to use. More partitions means better write scalability. However, read scalability suffers because you now need to query more partitions to collect aggregate results. Using this approach means relying on the scatter-gather technique, fan out to multiple partitions, collect results, merge them together. And as you add more partitions, that scatter-gather operation grows in complexity. To make a well-informed decision about the right number of partitions, you'd need to benchmark your specific workload and find the balance point that works for your read and write requirements. Let's get into the wrap-up. If you have extra time in your interview, there are a few more topics worth exploring. First, faster retrieval. Right now, fetching a user's profile means hitting the database every time. We can speed this up by caching the user object in Redis using a hash, with a mapping of user ID to user object. That way, when we need to display a player's name or avatar alongside their leaderboard position, we're reading from memory instead of making a round trip to the database. Second, breaking ties. What happens when two players have the exact same score? We need a deterministic way to order them, and a clean approach is to sort by the timestamp of their last played game. The player who reached that score first ranks higher, which feels fair and is straightforward to implement. Third, system failure recovery. Redis is fast, but it's also a point of failure. If we experience a large-scale Redis outage and lose our leaderboard data, we're not necessarily starting from scratch. Because we're writing scores to MySQL, we have access to the write-ahead log. We can replay those WAL entries through an ad hoc script to reconstruct the leaderboard from the ground up, restoring the sorted set back to its correct state.